Picture a landfill, not the smell, though you know that smell, but the sheer scale of it. Mountains of color, orange rinds curing in the sun, yellow lemon halves, black spotted banana skins, the papery translucent membrane of a pomelo peel, baking flat against the earth. Billions of pounds of fruit scraps discarded every single year by households across the world, going nowhere but down. And here's what nobody tells you. Buried in those scraps is one of the most complex, nutrient-dense biological compounds your garden will ever encounter. Not in a fertilizer bag, not in a bottle from the garden center, in your kitchen trash. I want to be careful how I say this because it sounds like I'm being dramatic, but I'm not. When I started understanding what fruit peels actually contain at a biological level, I had to go back and reconsider almost everything I thought I knew about composting. The conventional methods we've all been handed, they treat peels like filler, like bulk, like something you toss in to hit a ratio and move on. What I'm going to show you today is something fundamentally different, something that unlocks what those peels were actually designed to do. And if you stick with me until around the 14-minute mark, I'm going to show you the specific preparation method that changes everything. Because most people skip it entirely, and that's exactly why they're leaving the best part behind. Let's start here. You've probably been told that composting is simple. Brown stuff, green stuff, water, wait. And you've probably also noticed that your compost, even when it's done, feels like it's missing something. Your plants grow, sure, but they don't explode with life. They don't look like those photographs of absurdly lush kitchen gardens. They get by. And somewhere in the back of your mind, you've wondered whether you're doing it wrong, or whether the gardening world has just been overselling what compost can actually deliver. Here's what's really happening. The modern composting guidance most people follow was largely shaped by industrial agriculture's need to process enormous volumes of organic material quickly and cheaply. Speed was the priority. Standardization was the goal. And in that standardization, something got lost. The careful, specific use of particular organic materials for particular purposes. Fruit peels were lumped in with everything else. Into the pile. Turn it. Forget it. But historically, they were used very differently. And the science behind that difference is something I've spent the better part of 3 years digging into. And I'm going to unpack all of it for you today. Here's the part that bothers me most. A standard bag of granular potassium fertilizer from a garden center costs anywhere from $12 to $20 for enough to treat a modest-sized plot. You're going to throw away the equivalent nutritional value in fruit peels every single month, and nobody told you. No one profited from telling you. Think about that. The global fertilizer industry is worth over $200 billion. Not $100 billion, 200. And it is built, in significant part, on the idea that soil nutrition is something you must purchase, that nature's cycles are inefficient, slow, and unreliable, and that the solution lives in a synthetic bag or a laboratory bottle. I'm not here to tell you that industry is lying exactly. Synthetic fertilizers work, but they work the way a sugar spike works. Fast, visible, temporary, and with consequences for what comes after. What I'm describing today is something different. It's slower to start, yes, but once it's running, it feeds your soil at a depth that no $12 bag can touch. So, where does this knowledge actually come from? This isn't something I invented. This is something I found, or rather, rediscovered, while reading through agricultural texts from pre-industrial farming communities in East and Southeast Asia, particularly in the Japanese practice known as bokashi-adjacent composting, and in older Korean natural farming traditions called hanbang nongbeop, where specific organic inputs were carefully matched to specific soil needs. In both traditions, fruit materials, the rinds, the peels, the membranes, were treated not as bulk filler, but as active biological agents. They were prepared, fermented, or applied in ways that were completely distinct from how you'd handle straw or wood chips. In the Korean tradition specifically, citrus peel, And I'll come back to why citrus is the most extraordinary of all the fruit peels in just a moment. Was used as a primary ingredient in what they called fermented plant juice, or FPJ, collected at specific times of year, fermented with a small amount of sugar or raw honey, and applied directly to soil or as a foliar spray. The results documented in those early agricultural records, rice yields, vegetable density, root mass, look almost impossible by modern standards. Almost. Here's where the science catches up to the tradition. Two mechanisms are at work when fruit peels interact with soil, and both of them are operating simultaneously in ways that most backyard composting completely fails to capture. The first mechanism is potassium delivery. Fruit peels, especially banana, citrus, and apple, are extraordinarily high in potassium. Not the synthetic potassium chloride your garden center sells, which is water-soluble but can salt your soil over time, but plant bioavailable potassium in organic form, bound to carbon compounds that release slowly into the root zone. Think of the difference this way. Synthetic potassium is like dumping a bucket of water on a plant. It's all there at once, and what the plant doesn't grab immediately runs right through. Organic potassium from decomposed fruit peel is more like a slow drip irrigation line running through the root zone. Steady, consistent, and available precisely when the plant's biological processes call for it. Potassium is the element responsible for what plant scientists call osmoregulation, the process by which plants move water and nutrients through their tissues. It's the pump. When potassium is abundant and available in the right form, plants are more drought-resistant, more disease-resistant, and they produce more sugars, which is why fruit grown in potassium-rich soil tastes better. That's not anecdote. That's biochemistry. Banana peels contain anywhere from 3.5 to 4.8% potassium by dry weight. A single banana peel, fully composted, releases enough potassium to meaningfully shift the nutrient profile of several liters of soil. Now, multiply that by a season's worth of peels. You're talking about a genuine intervention, not a supplement. The second mechanism is what I find even more fascinating, and this is where the fruit peel story gets genuinely surprising. It's not just about nutrients. It's about microbial recruitment. Fruit peels contain high concentrations of simple sugars, volatile compounds, and specifically in citrus peels, something called D-limonene, which is the compound that gives orange peel its sharp, bright smell. Now, here's the counterintuitive part. D-limonene is actually a mild antimicrobial in its raw form, which is why you might assume it would harm soil biology. And here's your wait what moment for this section. In controlled studies examining fermented citrus peel compost versus unfermented citrus peel, researchers found that the fermentation process converts D-limonene and related terpenes from antimicrobial compounds into prebiotic compounds that selectively feed beneficial soil bacteria, specifically strains of lactobacillus and certain bacillus species. The very thing that makes orange peel slightly hostile to microbes in its raw state becomes a selective food source for the microbes you most want in your soil once it's properly broken down. That is not a small thing. That is a complete inversion of what most gardeners assume. And it's the reason that raw citrus peel dumped directly into compost often breaks down slowly, and sometimes sets back the microbial activity in the pile temporarily, while properly prepared citrus compost supercharges it. I want to spend some time here on exactly what properly prepared means, because this is where the practical application splits dramatically from generic composting advice. And I want to be clear, there are multiple approaches, and the best one for you depends on your situation. But I'll walk you through the core method first, and then give you an advanced variation that will genuinely change what your garden is capable of. Let's start with the base science. The cell walls of fruit peels are made of a compound called cellulose, and in the case of citrus specifically, they also contain pectin, a complex polysaccharide that is extraordinarily water retentive. Pectin is literally used as a thickening agent in jams and jellies. When pectin breaks down in soil, it behaves like a sponge matrix. It holds onto moisture and creates what soil scientists call aggregate stability. Aggregated soil has better structure, better aeration, better drainage in wet conditions, and better moisture retention in dry ones. It's the physical architecture of healthy soil, and pectin-derived compounds are one of nature's primary builders of it. But pectin doesn't break down easily in a cold or dry compost pile. It needs both microbial activity and slight acidity to decompose effectively, which means a compost pile that's running cool, which most backyard piles are for most of the year, is not converting pectin efficiently. The peels sit there, intact longer than you'd want, and the microbial bloom that should be happening is delayed. This is where pre-processing changes everything. And I'll come back to exactly how to do it in the practical section around the 14-minute mark. Stay with me, because I want to make sure the science is solid first, so the process actually makes sense when you see it. There's a study I keep coming back to, published by researchers at the University of Córdoba in Spain, working within the context of Mediterranean circular agriculture. They were looking at the composting efficiency of citrus waste specifically, which is a major agricultural byproduct in southern Spain and northern Morocco. What they found was that citrus peel compost that underwent an initial fermentation stage, even a brief one, as short as 10 to 14 days in anaerobic conditions with a small sugar inoculant, produced final compost with nearly 40% higher microbial diversity than aerobic composting of the same material. 40%. And the bioavailability of potassium in the fermented compost was measurably higher, which means not just more nutrients present, but more nutrients accessible to plant roots. That study was published in 2019. It confirmed in a controlled academic setting what Korean natural farmers had been observing empirically for generations. The tradition was right. It just didn't have the vocabulary for it yet. Have you ever tried fermenting your food scraps before composting them? Tell me in the comments. I genuinely love to know how far along people are with this, because the responses I've gotten on previous videos surprised me. Let's talk about one more mechanism before we move to the practical section, because this one deserves its own moment. The role of citric acid and malic acid, the organic acids that give fruit their tartness, in soil pH management. Here's what most people don't realize. Even though lemons and oranges taste extremely acidic, their ash, the mineral residue left after the organic matter breaks down, is actually alkaline forming in soil. This is because the acids themselves are metabolized by soil microbes, leaving behind potassium, calcium, and magnesium in mineral form. So the peel goes in acidic, the microbes eat the acids, and what's left behind shifts the soil in a mildly alkaline direction, while simultaneously releasing those three minerals. Now, for most garden soils, which in temperate climates tend to drift acidic from rain and organic decay, this is a benefit. It's a gentle, self-regulating buffering effect. Your soil's pH fluctuates less dramatically, which means nutrient uptake is more stable across the season. For soils that are already alkaline, common in arid and semi-arid regions, you'd want to balance your fruit peel compost with higher proportions of acidic inputs like coffee grounds or conifer needles. But that's a refinement, not a restriction. Apple peels and cores, for their part, contribute differently. They're high in malic acid and pectin, lower in limonene. They decompose faster and more completely in a traditional aerobic pile, but their pectin contribution to soil structure is significant. Grape skins contain resveratrol precursors that, and here is your second wait what, for today, have been shown in a small number of soil biology studies to support the growth of mycorrhizal fungi, the underground fungal networks that serve as an extension of plant root systems, allowing plants to access nutrients and water from a far larger volume of soil than their roots alone could reach. Grape skins in your compost may literally be building the underground highway system your plants depend on. I want to be honest with you. The mycorrhizal research on grape skins is preliminary. I'm not going to overstate it. But the biological plausibility is there. The mechanism is understood, and it's consistent with what we know about how polyphenols interact with fungal systems in forest soils. Keep your grape skins. Don't throw them away. All right, let's build this. Here's exactly what you'll need and exactly how to do it. And I want to be honest about what this asks of you, because it's less work than you think, and considerably more effective than what you're probably doing now. You're going to need fruit peels. Start collecting them. Any combination works, but if you want to optimize, prioritize in this order: citrus rinds, orange, lemon, grapefruit, lime first, banana peels second, apple skins and cores third. Everything else is a bonus. Mango, pineapple rind, papaya, all excellent. The more diverse your peel mix, the richer your microbial recruitment will be, because different peels feed different microbial populations. You'll need a container with a lid. A 1-gallon glass jar works perfectly. So does a food-safe plastic bucket. I use a 5-gallon fermentation bucket with an airlock. These run about $8 to $12 online. But you don't need the airlock. A regular lid with a small hole punched in it, or even a lid set just slightly ajar will do. You'll need a small amount of sugar. Raw cane sugar, molasses, or raw honey. Any of these work. The sugar is not feeding your plants. It's feeding the bacteria you want to cultivate in the fermentation process. You need approximately 1 tablespoon per pound of peel material. The cost is essentially zero. Optionally, and this is the advanced move I'll explain in a moment, you can add a small amount of active culture starter, whey from plain unsweetened yogurt, or a splash of raw apple cider vinegar with the mother. This seeds the fermentation with the exact microbial strains you want. Here's the process, step by step. First, chop or tear your peels into pieces no larger than 2 to 3 centimeters. Size matters here. Surface area determines how quickly microbial colonization begins. Larger pieces decompose slowly. Small pieces ferment fast. If you have a blender or food processor, you can pulse them into a rough slurry, which accelerates the process dramatically. You're looking at fermentation completing in 5 to 7 days instead of 10 to 14. Pack them into your container, not tightly. You want some air pockets initially. Dissolve your tablespoon of sugar in about a quarter cup of water and pour it over the peels. If you're using the starter culture, add it now. A tablespoon is plenty. Press the material down, put the lid on, and place it somewhere warm. Room temperature is fine. A spot near your kitchen radiator or water heater is better. You're looking for somewhere between 20 and 30 degrees Celsius. That's roughly 68 to 86 Fahrenheit. That temperature range is where lactobacillus bacteria thrive. Within 24 to 48 hours, you'll start to see bubbling. This is CO2 from microbial metabolism, and it means the fermentation is working. The smell will shift from fruity to slightly tangy, then to something that resembles a mild, almost pleasant sour, like citrus yogurt, if you can imagine that. What you don't want to smell is putrefaction, rot, ammonia, or sulfur. Those smells indicate anaerobic decomposition by the wrong bacterial strains, usually caused by too much water. If that happens, add more dry peel material, aerate briefly by stirring, and add a small pinch of salt, which will suppress the unwanted bacteria without killing the beneficial ones. Most people get this wrong in one of two ways, so let me address them directly. The first mistake is adding too much water. Your peel mixture should be moist but not wet. If liquid is pooling at the bottom of your container, you've added too much. The material should feel like a wrung-out sponge, damp enough that you could squeeze a few drops from it, but not dripping. Too much water creates anaerobic conditions that favor the wrong bacteria and will give you rot instead of fermentation. The second mistake is opening the container too frequently to check on it. Every time you open it, you let in oxygen and disrupt the microbial environment that's trying to establish itself. Particularly in the first 3 days, leave it alone. Check it once on day 2. Just open, assess smell, close. That's it. After day 5, you can start checking daily. After 10 to 14 days at room temperature, or 5 to 7 days if you used a blender and a starter culture, your fermented peel material is ready. It will have shrunk in volume by about 30 to 40%. It will smell sour and earthy, not rotten. And it will have transformed, at a microbial level, into something quite different from what you put in. Now, you have two application options, and they serve different purposes. Choose based on what your garden needs. The first is direct soil incorporation. Dig fermented peel material into your soil at a ratio of approximately 1 part peel compost to 8 parts soil at a depth of 15 to 20 centimeters. This delivers the potassium, the pectin, and the microbial populations directly into the root zone. Do this in the fall for spring plantings, or at least 4 weeks before planting in spring. The microbial populations need time to integrate into the existing soil ecosystem before your plants go in. The second option is liquid extraction. Take your fermented material and dilute it in water at a ratio of 1 part fermented peel to 10 parts water. Stir well. Let it settle for an hour. Then apply as a soil drench, poured directly around the base of existing plants. This is what functions closest to the Korean FPJ method, and it's extraordinarily fast-acting. You can do this with established plants throughout the growing season, roughly every 3 to 4 weeks. The potassium and organic acids go straight into the root zone in a form that's immediately bioavailable. For experienced gardeners, here's the advanced variation. Layer your fermented peel compost with wood chip mulch at the soil surface, rather than incorporating it. The mycorrhizal and bacterial populations will colonize from the fermented layer downward through the wood chip interface, gradually building a living biological soil amendment that continues working long after the visible material has broken down. This is a technique borrowed from Korean forest farming, where the interface between decomposing organic material and mineral soil is understood as a uniquely active biological zone. So, what does your garden actually look like after all of this? I want to be honest with you about timelines, because the gardening world has a persistent problem with overselling quick transformations. In the first week after soil incorporation, you will not see dramatic visible change. What's happening is invisible. Microbial populations shifting, establishing, colonizing. If you've added the liquid drench to existing plants, you might notice within 10 to 14 days that leaf color deepens slightly, particularly in plants that were showing any signs of pale or yellowing lower leaves, which is often a potassium deficiency signal. This can look like a subtle richening of the green, a more saturated color in the newer growth. It's not dramatic, but it's real. By week 4 to 6 in soil that has received direct incorporation, you should notice improved water behavior. The soil holds moisture better after rain and dries out more slowly between waterings. This is the pectin matrix beginning to establish aggregate structure. If you scratch into the soil, you'll start to see the dark, crumbly, almost chocolate cake texture that indicates active microbial life. That texture is not cosmetic. It is the physical manifestation of soil health. By month 2, particularly if you're growing vegetables in amended soil, the difference becomes difficult to miss. Root vegetables, carrots, beets, turnips, will show markedly improved yields in the first season. Fruiting plants, tomatoes, peppers, cucumbers, will show improved fruit set, more consistent sizing, and, if you taste them, richer flavor. That's the potassium. You can taste it. There will be a phase, usually around week 2 to 3, that can alarm first-timers. The soil surface may develop a white, slightly powdery or fuzzy appearance, particularly around where you've incorporated the peel compost. Most people see this and assume something has gone wrong. It hasn't. That white growth is fungal mycelium, the root threads of beneficial soil fungi. It's a sign that the biological amendment is working exactly as intended, that the fungal community is colonizing the new organic material. It will recede as the fungi move deeper into the soil profile, following the decomposing peel material downward. Leave it. Don't rake it. Don't panic. It is, in fact, one of the most encouraging signs you can see. What might actually indicate a problem? If your plants develop crispy, brown leaf edges that spread inward, particularly in combination with soil that smells sour, or off even weeks after application. You may have over-applied or applied material that didn't complete fermentation. This is almost always the result of rushing, applying material that was only partially fermented. The fix is simple. Dilute with water, add organic matter, and wait. The soil biology is remarkably resilient if you give it time. Here's what this really means, stepping back from the specific technique for a moment. You have in your hands, every single week, one of the most biologically sophisticated amendments that your garden soil can receive. Not something you need to buy, not something manufactured in a facility in another country and shipped to a warehouse and marked up 3 times before it reaches you. Something your kitchen generates as a byproduct of the fruit you eat for your own health. The knowledge of how to use it was never lost exactly. It was scattered. It lived in traditional farming texts that were never translated, in agricultural practices that were disrupted by industrialization and colonization, and the economic logic that made buying easier than knowing. It survived in corners of the world where self-sufficiency was never a choice but a fact of life. And it is, without any exaggeration, more powerful in its cumulative effect on your soil than almost anything you can purchase. Share this with someone who has a garden and throws away their fruit peels, because that's a lot of people, and every one of them is discarding something extraordinary. The gardener who understands this is not going back. There is something that shifts when you realize the system of dependency you've been operating inside isn't necessary, that the loop of purchase, apply, deplete, purchase again has an exit. The exit is knowledge. Specifically, knowledge that the industrial food and agriculture complex has very little financial incentive to hand you, because your self-sufficiency is, by definition, not a revenue event for them. I'm not asking you to distrust everything or to reject all of modern horticulture. Some of it is brilliant, but I am asking you to look at what's in your kitchen trash before you close the bag, to understand that the bright orange rind, the rubbery yellow peel, the papery membrane you never think twice about, these are not waste. They never were. We were just taught to treat them that way. What you do with a fruit peel in the next year will not change the world, but it will change your soil. And changed soil grows different food, better food, more food. Food with more flavor, more density, more life. That matters. Not abstractly, concretely, in your garden, in your kitchen, in the bodies of the people you feed. That's worth knowing. It's worth doing. And it's the kind of knowledge that compounds. The more you practice it, the more you understand. The more your garden teaches you things no YouTube video can. If you haven't subscribed yet, I'd ask you to do that now, because what we're going to look at next week goes even deeper into traditional fermented inputs, and specifically into the one preparation that can transform a struggling, compacted suburban plot in a single growing season. We're not done unearthing what's been buried, not even close.